Hello. In this lecture, we're going to look at metabolism of monosaccharides, namely focusing mostly on glucose. To get right into it, I want to first touch on digestion of complex carbohydrates to monosaccharides. This is a depolymerization reaction where you convert the complex carbohydrate, the polysaccharide, into its monosaccharide, the polymer chain made up of monosugars, I guess, back to those monosugars. And so to get into that, what we want to do first is look at the types of connection points that we could see. So typically we see 1, 4, and it's 4 prime glycosidic linkages, where the O on C1 connects to C4 of the other monosaccharide. Okay, so let's move away from the words now and get into the actual chemistry. So let's draw some structures. We'll take some chair structures to start, and then we'll move into like a few simpler structures. These are kind of tedious structures to draw. Okay, so this is going to be a maltose unit. Okay, so what I'm going to do is just draw the axial position to an O. That's going to connect to the equatorial position of the second sugar. And now with all the remaining substituents that aren't at that anomeric carbon, with all of those being, excuse me, let me finish this. So, and there we go. Okay, so all of the other carbons are going to have equatorial substituents, excluding the axial group, where we have a linkage that has an, except for the anomeric position, which has an axial linkage. Now this linkage connects from the anomeric position of the first carbohydrate, which is defined by C1. Now if we count around the ring, we've got 2, 3, 4, 5, and then the CH2 appears 6. Okay, so we say this is a 1,4 linkage because we're connecting from carbon 1 on the first saccharide to carbon 4 on the second saccharide. Okay, so that's one type of linkage, and it's called a glycosidic linkage. And this would be an alpha 1 4 prime glycosidic linkage, because at the 1 position, that's the anomeric carbon, this is an alpha anomer, that alpha kind of diastereomer, alpha for axial, that sort of thing. We have an axial arrangement at C1. Now C4 is, for this particular saccharide, which is glucose, we're going to always kind of see that C4 position equatorial. Everything is equatorial except the anomeric position could be axial for the alpha anomer, or beta for, equatorial for the beta anomer. Okay, and that was from the last lecture and that sort of thing. Okay, so that's one type of linkage. We could also have a 1 to 6 prime, and this is called a glycosidic. If the last one was a glycosidic link, this is called a glycosidic branch because it leads to branch points in complex carbohydrates. So what we're going to do is consider our chair structure, but now the 1 position, which is shown as the kind of slanted downward, we'll have the alpha version. That's now connected to a CH2. Let's see, how do I typically draw this? To a CH2 of the second chain. Okay, so there's my CH2 group, which goes up to an O, down to the anomeric position, and we have equatorial OHs. That's terrible right flap for So there's one side and there's the other side of our polymer. Okay, so the point is here, we're connected at the 6 position from the 1 position. And so 6' would be prime, meaning it's the opposite. It's the other kind of saccharide that's positioned. Okay, so anyway, those are the 2 types of linkages that we typically see. The book discusses those in a little bit more detail. Now what I want to do is move into, so it's kind of that CH2 OH is that 1 to 6 branch point. Okay, so what I want to do is cover kind of the general approach for hydrolyzing these complex carbohydrates back to the monosaccharides. And that's really going to be looking at the hydrolysis of the links in the branches. So what I'm going to do is just have a single monosaccharide. And I've got my O to an R group. I'm just going to put that R group kind of looking like it's going equatorial. My C6OH, C3OH, and then my C2OH. Okay. So what I'm going to do is, first of all, we're going to let this O engage in H plus from something else. It's typically the acid residue, an acid residue within an amino acid active site. These things don't just automatically fall off, but we're going to let the oxygen that's attached to the anomeric position engage that hydrogen atom. And actually, it might be just a little bit more practical. I'm going to drop the lone pairs, and I'm just going to show the bond. Gosh, I hate this. I hate this OH right here. Okay. Clean this up so you can see that one. Okay. I'm going to take the electrons in this covalent bond and engage that H within the acid active site. And that is going to be propelled forward by donating the lone pairs in. So we're going to kind of bring the lone pairs of the of one anomeric oxygen down to add to an acid. And this is really the first step in the reverse process of converting acetals back to carbonyls. But anyway, when we do that, what we get is we break that bond between the acetal carbon and our anomer oxygen, and we get a carbocation at this position, excuse me, an oxocarbenium ion, or just a cation on oxygen, okay, which can now engage water, again, through an enzyme active site from either the top face. So what I'm going to do is I'm going to show a lone pair on water, adding to either the top face for the beta attack, and beta is again equatorial, or the bottom face to give rise to an axial OH ultimately. And that bottom face is going to be axial for alpha, so that's going to be alpha attack. Now, in both of these cases, it's a little bit cumbersome, but we do need to think about an enzyme sort of grabbing a hydrogen, which facilitates the addition of the oxygen, making it more nucleophilic so it can add to that carbon atom and then push the electrons onto the oxygen to neutralize it. So either one of those attacks would give rise to either one of the anomers, that is alpha or beta, axial or equatorial, at that anomeric carbon. So I'm just going to show it as an ambiguous squiggle here. So both the alpha and beta are possible. Okay. Now, that is a nice first look. But what I want to do now is I want to kind of take, this is the first step. We have to kind of clip down the carbohydrate into some smaller molecules like monosaccharides, and so it's just like a hydrolysis of an acetal back to a hemiacetal. Kind of touched on this a little bit in Organic 1. other than kind of the involvement of the enzyme active site in various places, it's a reaction that's kind of from organic too. You take acetals, and if you have water in excess along with an acid catalyst, you're going to go back to the hemiacetal and ultimately back to the aldehyde. Because these hemiacetals are formed by an intramolecular attack, we're not going to see them go back to the ring open formed in any great degree, at least from this structure. Okay. Now what we're going to look at is the breakdown of glucose. So this is going to be glucose catabolism, which again, catabolism, these are the steps within metabolism that lead to the breakdown of the biomolecules that we're looking at to get to smaller molecules. This has a specific name, glycolysis. So glycolysis, if you think about it, you can see glyco for glycogen, some sugar or something, and lysis meaning to break down. We're going to focus on glucose catabolism, or glucose catabolism, or glycolysis, although this general approach to breaking down glucose can be used with other types of sugars as well. Okay, so let's go through the big picture steps, where I just kind of tell you what happens. Then we're going to dive deeper into a few of the really interesting steps that have some curly arrows to look at. Okay, so we won't be drawing this chair structure for long, just a few times, because we're going to break the chair. Okay, so I'm going to take glucose, and I'm going to react it with ATP to put a monophosphate on one of these positions. It turns out it's going to be C6. If you recall, 1, 2, 3, 4, 5, 6. We're going to react this with ATP in what's called a phosphorylation reaction, where we just add inorganic phosphate to make some sort of phosphate ester species. Now, this isn't adenylation. We're not carrying with us the adenosine group, okay? So it's just one phosphorus phosphorylation event happens. Now, what that looks like is we're going to take our chair structure and draw everything the exact same except the 6th position. Is going to now have a phosphate group, which I'll draw out because once you get the hang of them, they're not too bad. Okay, so there's our phosphate, and ATP gets consumed to make ADP. Okay, so this is glucose 6-phosphate. The book has the alpha version. I'm not going to differentiate the two. You could have the alpha or the beta going through here. Now, what this is going to do is this is going to isomerize, and we'll look at this mechanism in a second, but this is going to isomerize from the 6-membered ring to the 5-membered ring to make a fructose 6-phosphate. So now we need to draw a 5-membered ring. You can draw these kind of in what's a Hayworth projection, where you've got kind of a wedge coming down here, and then we just have, instead of axial and equatorial, we have up and down to consider. So we go up to CH2, OH, 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 OH. So if you look at all of these atoms so far, we have very similar alignment with glucose. These are just isomers of each other. We just have 2 CH2 groups instead of just the one like we did with the 6-membered ring. That one was at C6. Now we just have, I mean, I guess it's still 6. At the 6th position, we have a CH2, but also at, I believe, the, maybe that's carbon 1 over here. Better not leave that in the notes. I don't know that numbering scheme. I don't see it in the book. Okay. Anyway, now our phosphate is just over here. Okay. So this is now fructose 6-phosphate. Now I did specify the stereochemistry here just to match the book. You don't have to worry about the name, but you would call that the, sorry about that. I needed to generate some pages. You would call that the alpha version as well. And again, I don't want to worry too much about the 5-membered ring stuff. Let's just focus on the 6-membered ring. That's where sort of the meat in all of this is. Okay, so we're actually going to consume another molecule of ATP to install another phosphoryl group, another phosphate ester on our molecule. So we're going to do another phosphorylation. We're just sticking another phosphate on. It turns out it's at the other CH2 position, but we're now going to flip the stereochemistry at that position. So here's my Hayworth projection, just showing a few wedges. Don't worry about this too much. But now I'm going to have an OH up at the anomeric position on a CH2. And now this O was originally right here. So we flipped at the anomeric position to give us the beta isomer. And now we're going to add a phosphate group at this position. And then the phosphate group over here remains intact. Okay, and then we're going to put OH up, OH down. Okay, so this is a fructose bisphosphate. Now, the addition of that second phosphate triggers what's called a Retroaldol reaction. So what I need to do is I need to go back to the open chain form, because I'll be able to better see what's happening here. But in the open chain form, I'm going to show this as a Fisher projection, which has all of my crosses and that sort of thing. I realize that's a bit annoying. I'm just going to draw the phosphate group as a P with a circle around it. Okay, so there's one. Now I'm going to go H, OH, and then OH, OH to set the proper stereochemistry. So that's an O. I could do better there. All right. Okay, so went to all this work, and now we're showing the phosphate, the bisphosphate shown in the open chain form, not the equilibrium favoring position, but it allows us to see the break in the bond that's coming. So what we're going to do is sever this molecule in half by cutting at this position. So we're going to cut at that position. Now, if you want to see the general curly arrows and what they look like, this is actually going to be a Retroaldol reaction. So I'm going to show this. Some base comes in, grabs this hydrogen, push down. Now the electrons in the blue bond are going to come over and come up to give an enolate structure. The enolate can now pick up a hydrogen. We'll look at this mechanism in more detail in a little bit, but suffice it to say, we now get two species. Basically, we just cut that molecule in half. Now the two species we get are I believe this is just CH2OH. Okay, so this is called Gaap, or excuse me, Dhap, Dihydroxy Acetone Monophosphate. You can see it looks like acetone, but we've got two OHs, and one of the O's is a phosphate. Maybe you want me to draw that. I could do that. So there's a phosphate. There's an OH. So if you look, that looks like acetone with two hydroxy groups at the alpha position. One of the hydroxy groups has a phosphate group attached to it. It's like it's done a phosphorylation. So that's where the dihydroxy acetone phosphate comes in. Now, additionally, we're going to form an aldehyde. This is the bottom of the blue bond. So we have an aldehyde here because we made a carbon-oxygen double bond at a carbon that already had one hydrogen. Now we go to our OH and H. We still have a stereocenter present, and that stereocenter persists through this reaction. But what's cool about this is there's actually an enzyme that can isomerize both of these. And we'll look at that isomerization. But we go from DHAP, dihydroxyacetone phosphate, to a molecule called glyceraldehyde 3-phosphate, or glyceraldehyde monophosphate or something. Okay, so I call them Dhap or DHAP and Gaap. And so these molecules are sort of the building blocks that ultimately give rise to carbohydrates. And it's through this aldol process. We do an aldol reaction, a cyclization, rearrange some phosphates, and we get to a 6-membered ring. Rearrange, kind of losing the phosphates. Okay. But now what we're going to do is take Gaap and metabolize Gaap. So we cut the molecule in half to make DHAP and Gaap, and DHAP can give rise to Gaap. Now, both of those are involved in the catabolism and then also the biosynthesis of carbohydrates. But here we're going to break this down. So we're going to break down glyceraldehyde 3-phosphate, this molecule shown here, which can come from DHAP or just straight away from the open fructose 1,6-phosphate. And we're going to decompose that using an oxidation reaction, so NAD plus and phosphate. Let's just, well, yeah, I'll just write P with a circle around it. You can put a little I for inorganic phosphate. But anyway, we're going to take the glyceraldehyde 3-phosphate and we're going to oxidize the aldehyde. And phosphorylate the carboxylic acid position. So I'm going to have an oxygen atom now present in my glyceraldehyde 3-phosphate, my Gaap. And additionally, that oxygen is going to be phosphorylated. And so what that tells us is that right here, we've got an acyl phosphate, which is indeed unusual, especially with all of these kind of nucleophilic positions around. And indeed, it does not last long. What we're going to do is actually generate a molecule of ADP to make ATP, where adenosine diphosphate, remember, is the byproduct after ATP is activated. So we're going to charge an ADP to make our energy-rich ATP by consuming the phosphate at this position. Maybe I'll kind of highlight ATP and then highlight this arrow. So it's the acyl phosphate, that reactive phosphate, that reacts, and ultimately what we just end up with is the carboxylic acid version of glyceraldehyde 3-phosphate. Okay, so the glyceraldehyde 3-phosphate just gets oxidized over this 2-step sequence, but we also, in addition to doing that oxidation, we generate some ATP, which is what this is all about, energy building, that sort of thing. Okay, now additionally, what we're going to do is, now what we're going to do is isomerize this phosphate to form just a slightly rearranged structure where the phosphate has moved from an exterior OH to the interior OH. So the phosphate just jumps over to the internal OH and we have a CH2OH sitting out here. What we can do at this position is eliminate water by taking the alpha hydrogen and then pushing off net H2O loss. And we get a double bond in our structure. So our species now, it's getting a little awkward, but now we have a double bond right here. Maybe I could draw the CH2. If you're having trouble seeing that, here's the CH2. It's lost an OH. So we've lost water as a result of this reaction. Okay. And that gives rise to a molecule that I've heard the name quite a bit. So I'm going to write it out. This is Phosphoenol. You can see it kind of has an enol-like character to it with this O attached to a CH2 with a double bond, phosphoenol, and then an important word comes, this is all one word, pyruvate. Okay, so that enol is important to highlight here because what happens next is we are going to dump off that phosphate and charge another molecule of ADP to form ATP. So the ADP converts into ATP, and that's going to give rise, I'm going to draw this out, but you're not going to see any like real evidence of this product forming to an appreciable degree, because now we have, I'm going to put that in brackets so we can highlight that this is an intermediate, and now we have an enol. Highlight that in blue again. And the enol is going to readily tautomerize to a very unusual structure where we have if you look at this, we have 1, 2, 3. So this is like a 2 keto propionic acid, or 2 oxo propionic acid. Well, nobody has, I think I may be the first person ever. No, of course not. Nobody calls this 2 keto propionic acid. This is an important molecule called pyruvic acid, or pyruvate. So this is going to be buffered at aqueous, or excuse me, physiological pH to form the carboxylic acid form. And basically it's an alpha keto acid. So you put a ketone at the alpha position of a carboxylic acid, and then we have a methyl group at the beta position. So this is pyruvate in its deprotonated form. And that's preferred that we call that pyruvate. Okay, so that is catabolism. That is glycolysis, the conversion of glucose back to pyruvate. In a future lecture, we're going to look at the different things that pyruvate can do. It's pretty super interesting molecule in its own right. It does some really cool biochemical reactions. But just stopping here, let's take a second. Let's take a second and go through some of these critical steps. The first one I want to go through is sort of a closer look at hexose, which is a 6-membered ring to, or let's just call it glucose to fructose interconversion. Hexose to pentose. Hexose to pentose is fine. Let's just stick with hexose to pentose. Okay. So what we want to do is go from a 6-membered ring, which everybody loves drawing hexagons, to a 5-membered ring. These are a little bit more, these 5-membered rings are, as you can tell, much more awkward to kind of show in a, a stereochemical depiction like a chair structure or something. So let's look at this now. What I want to do is look at the open, I want to take my glucose, let's take our glucose and recall what we're working with here. We have glucose 6-phosphate. So there's my 6-phosphate. If it's glucose, everything is equatorial. Okay, now what I want to do is go to the open form. Now the open form is going to convert this anomeric CO bond into an aldehyde, and then it's going to disrupt this bond that I've highlighted in red. Okay, the book draws curly arrows. I just want to be a little bit careful before we go down that path. So I'm really just trying to draw the chair structure just as I saw it previously. Just now I have an aldehyde and an extra OH. So now I have my open form glucose, and whoops, I have a phosphate I need to include, don't I? So this is open glucose 6-phosphate. Okay, so I have my open form of glucose 6-phosphate. what I can do is actually recognize that if I have an aldehyde, I could potentially deprotonate this. So I'm just gonna have some base come in. And this is definitely facilitated by some sort of acid residue or some sort of acid something floating around. So I'm gonna have this negative charge come up and grab an H instead of just letting it sit around as an enolate, which would not be stable at physiological pH. And indeed, that's a glutamic acid residue. Okay, so we now have our structure. Did I draw? I did. I drew too many OHs at one position. Sorry about that. I was like, gosh, why am I already off to a bad start? Okay. Now I see. So now I have an enol. Now, I do have an enol across here, which is what I just made by that kind of tautomerization event. But I also, if you look, I also have an enol across here. So I sort of have like this double enol. It's just a dihydroxy alkene. I say just. What that means is that when we have tautomerization, we go from the enol back to the keto form, we can actually generate a keto using either one of those oxygen atoms. And in fact, we're actually going to tautomerize through the red. We're going to tautomerize through the red to, once again, give our structure. Now this time, that O at the end is now an OH because our red carbon, our red bonds participated in tautomerization to give a keto form. Well, if the keto form exists, then if we form the ring closed form, we would have to grab our usual C5 hydrogen to put an oxygen 6 atoms away from C1 into the carbonyl. But this time, that oxygen at the 5th carbon is going to attack into C2, giving rise to a 5-membered ring because the oxygen is like the 6th element. So instead of making a 6-membered ring, we go 1, 2, 3, 4, 5 to make a 5-membered ring. And I'm just going to go ahead and draw it this way. And we could have CH2OH, OH here, and then we go up, down, up, CH2OP. So there's our isomerization from a 5-membered ring to a 6-membered ring, where the bond that was formed is this bond here. And there's our 5-membered ring. Okay, so that was one of the reactions I wanted to look at. The other one I wanted to look at was the Retroaldol reaction. I mean, I did kind of, maybe I spelled that out well enough. I mean, it's got some really deep, it's got some really cool mechanistic intrigue. What I'll do is I'll set us up. I'll set us up so that we can see it a little bit better. So the Retroaldol reaction. So this is going to be a closer look. Retroaldol to, remember those two molecules, we had glyceraldehyde monophosphate and dihydroxy acetone monophosphate. Two separate molecules. Okay, so what I want to do is get the Fisher projection back in front of us, where we have a phosphate at this position. Now we have a ketone at C2. Then we go left, right. I'm going to run out of space, aren't I? Oof. Okay, well, look at that. Okay, we got it. Oh no, this is the diphosphate. Right, because we split off into two molecules, each with a phosphate atom. Okay, so what we have to do is we have to clip this molecule in half. And by in half, I mean in half. Okay, so if we look, we've got 6 carbons. We're going to cut it in half to 2, 3 carbon bonds. So what we have to do is find a way to do a retroaldol reaction where we deprotonate an alcohol and then cleave a carbon-carbon bond. This is the opposite of an aldol reaction in every way. Now to do that, we have to activate the molecule so it's more likely to undergo a retroaldol reaction. To do that, we engage an enzyme active site that has a free lysine residue. And the lysine is at position 229 of this particular enzyme, but we have some sort of lysine residue, which is a long chain into an NH2. And what we do with these is we form Schiff bases or imines. And so the book goes through like the imine mechanism. And remember, I wanted that to be as automatic for us as ketoenol tautomerization. So let's just go ahead and let it be automatic, where we have CH2O phosphorus now adducted to a carbon that is an imine. Now they have the imine going in the opposite way. I'm just going to put an E for ENZ for enzyme. Okay, they have the imine going in the opposite way. That's fine. There's no stereochemistry we have to worry about too much that we can actually glean from this picture. But now, so it's 1 left, then it's 2 rights, and then it doesn't matter. Okay, so now we're activated a bit. We can have hydrogen bonding here. Let's go ahead and leave the hydrogen bonding present. So hydrogen bonding to the imine is going to make that an iminium ion so that it's activated. What I'm going to do is just pick on this first hydrogen on the OH on the first one on the right, and we're going to let that react with the base now that it's activated, where we deprotonate, push electrons in from the carbon-carbon bond, breaking the carbon-carbon bond, and then making a, in this case, it would be an enamine just for a moment. So when we do this reaction, we do the retroaldol reaction. We form something a bit more stable now than we did previously, because instead of generating an enolate under biological conditions, now we have like an enamine that's neutral. Okay, what does that enamine look like? It's going to be, there's our N with our enzyme and our H, and then we're going to have our CH2O phosphate, and that's plus the aldehyde that we formed all along. If you recall, the aldehyde is the glyceraldehyde monophosphate, the Gaap. And that's what we're going to take forward. Just looking up the name of that enzyme. I shouldn't get ahead of myself. Okay. Gosh, that enzyme, I just need to know the name of it. Okay, anyway, we're here. At this point, we can react this with H2O. I can put H2O over the arrow to give DHAP. Now we keep going with Gaap, the glyceraldehyde monophosphate. The dihydroxy acetone phosphate has a ketone in the central position. But this, it's just not the way the mechanism works, though. And I just want to know the name of this enzyme that converts the DHAP into glyceraldehyde 3-phosphate. And oh, I know it starts. Okay. I'm going to let it go. I'm going to let it go. Okay. That's too bad. But those things are pretty easy to show, so we can just mention that briefly before we go into interconversion of DHAP into Gaap. We can just show this before we get into glucose biosynthesis. Okay, so let's go through this now. What happens here is we take, gosh, I really just want to know what this enzyme is called. I know it's right here. I just read it. I'm so sorry. I'm so sorry. All right, forget it. It's over. All right, so what we're going to do is take DHAP, and we're going to react it with an enzyme active site using pretty simple chemistry. What you do is you've got, let's label this COH. We're going to label this with some explicit hydrogens. That's connected to a ketone. That's connected to a CH2OP. Now what we do is we let a basic residue and an enzyme come in, deprotonate, make a formal enol, an enolate, but this probably adducts to it's probably hydrogen bonds to an enzyme in the active site, or to a residue in the active site, to give us this species. Okay, so we're hooked up to the enzyme by way of this enolate. And now what the book proposes is that what we do is we take these electrons and we reach over and grab this hydrogen, push the electrons down, and then push these electrons over to grab another H that's adducting to the enzyme. So what this is we have another enol form between two hydroxyl groups, and that allows us to push things at the end of a chain as an aldehyde, or carbonyls inside the chain as a ketone. Okay, so when we do this, we get Gaap. Okay, so there is the catabolism of glucose. Now let's go backwards in time, and we are going to take, once I find it, we are going to take our pyruvate. So Gaap ultimately ends up as pyruvate after several steps. We're going to take pyruvate and go back in time and get all the way back to glucose. Okay, so this is going to be gluconeogenesis. So overall, we're going to take pyruvate and we're going to go to glucose. So mostly the opposite, with sort of one twist here. We need to pull on some CO2, and that's going to start right away. So what we're going to start with is this fun molecule, which is the conjugate base of pyruvic acid. So we call that pyruvate. We're going to react that with ATP, CO2, and H2O. And what we're going to do is like an aldol reaction on CO2, sort of. Let's see. Well, yeah, kind of. Let's not get too let's not get too deep into it right now. Okay, so what's going to happen here is we're going to make a new molecule where we've adducted the CO2 onto the methyl chain. I mean, it's an aldol reaction on CO2 where we generate this bond. And we'll look at that in closer detail. That'll be the only reaction from this pathway that we look in greater detail. But let's go ahead and go on with this. So from here, well, I guess I also want to look at this reaction. This reaction is fun. We're going to then lose CO2. We are then going to lose CO2, and we are going to convert something like ATP, which is GTP, into a phosphate. Okay, so what do we get at this point? What we form is the phosphoenol pyruvate that was an intermediate, a late stage intermediate in the formation of pyruvate from glucose. Okay, so now we start going back in time. We're going to have H2O add back, before it was removed or eliminated to make the double bond, we're going to add it back in to remake the hydroxylated species. And so that looks like this. And you can think about that as though we're doing like a beta addition to a carbonyl, if you want, with a hydrogen transfer at the end. Okay. This was the point to make this intermediate in our glycolysis pathway. We had to do a phosphate migration. So we're going to do the opposite of that here, moving the phosphate from the inside oxygen to the outside oxygen. Okay. So there we just swap places the phosphate and the carboxylate stays the same. Now it's at this point that we need to do we need to synthesize, or we need to put a phosphate at the end of the chain on the carboxylic acid group, and then we need to reduce that to an aldehyde. So we're going to add some ATP in, and the ATP is going to provide a phosphorus group. Okay, there's our phosphorus group. Now we have an acyl phosphate, which is an excellent electrophile, and it can actually be, it's a super cool reaction. You can just reduce this with like the equivalent, biology's equivalent of a hydride reagent, which is NADH, and then an acid too, and we can actually take this down to the aldehyde. Well, I don't expect you to have these structures down after the first lecture, of course. These are some of the most complicated structures in all of biochemistry. I mean, I guess nucleotides get there, but it's all because of the sugars. But anyway, if you're tracking this kind of well, you might stop and smell the roses and realize that we're at the glyceraldehyde monophosphate. So we're halfway done. We've got our Gaap made. Gaap can be interconverted with DHAP, dihydroxy acetone phosphate, by that mechanism we just looked at before we started this pathway. So there's our interconversion of DHAP. Now what we need to do is take DHAP and Gaap and add them together in an aldol reaction. So we need to take a Gaap plus a DHAP enolate, okay? And when we add these together, here's what this kind of looks like. I'm going to flip my DHAP over, and I'm going to draw the enolate of it. It's not the actual enolate. It's something that's activated and behaves like it that does the aldol reaction. So hopefully you can kind of appreciate that. But I do have an enolate here that I'm just drawing for the purpose of, hopefully you can start to see this. I may be asking too much of you. Sorry if that's the case. But anyway, we're going to do this once. We're going to do an aldol reaction where the enolate adds to the carbonyl and pushes the electrons up. And then, of course, we have all the hydrogens we need. There's not a full-blown enolate, but there's something that behaves a lot like it in the enzyme active site. I just wanted you to see what we get after we do this. Well, after we do this, all stereocenters controlled. We now have a bunch of hydroxy groups. Okay, so there's the new bond. Oh my goodness, we're really like wrapping around here. All right, so we have 3 hydroxy groups in a row. Well, actually, what this is sorry, this is a CH2 phosphate. If you look, this is 1, 2, 3, 4, 5, 6 atoms. By doing that aldol reaction, we are at all of the carbon atoms that we need to make glucose. Okay, so what's going to happen now is, well, we're going to say we're almost there, but the carbonyl is in the wrong position. Shoot, we have to get rid of that phosphate at C1. In the meantime, what's going to happen is the hydroxyl group at C5 is going to come in, because the hydroxyl group at C5 sees all the carbonyl action. We're going to steal its OH electron density and add to the carbonyl, which then grabs an H, and that's going to form a 5-membered ring. And according to the book, this is the stereoisomer that we get. Okay, and then it's up and down, right? Up. So this is that 1,6-bisphosphate. What we have to do is kill this phosphate at this position, which will allow us to isomerize to the 6-membered ring. So we're going to kill this. Now, if this is open, we're going to make the 6-membered ring. If that's open, we're going to make the 6-membered ring. So you could decorate this all you want, or you could jump to a chair structure, which maybe at this point everybody's like yearning for because these 5-membered rings just get so awkward. Okay, let's get to the 6-membered ring. So open, we're going to ring open, and then we're going to close. It's really 3 steps, but I'm getting too excited because we're almost done. We're going to open, we're going to tautomerize, and then we're going to close. These are the 3 opposite steps that we did previously when we had our 6-membered ring. But if you recall, we're not at glucose quite yet. Equatorial, 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 CH2OP. We have to get rid of that phosphate. So lose the phosphate to get to the structure that's a 6-membered ring. Holy cow. The people that say this isn't a real class. We just did the biosynthesis of glucose. We did it. Okay. So one of the most complicated, yet one of the most important metabolic pathways, both glycolysis to break down the catabolism of glucose back to pyruvic acid, back to pyruvate, and then the metabolism of pyruvate back up to glucose. This is very applicable to other sugar pathways. We're going to look at some specialized sugar pathways going forward, but you know, I know this is a ton of work. It's a ton of work to do. You should be doing it in biochemistry is my guess. If you're not, then for all of you that are taking the MCAT, you're welcome. So hopefully you're welcome. Maybe you didn't find this helpful at all. But you know, here's kind of an overview of the topics. At least there was enough commentary to give you a sense of what's happening and sort of why it's happening. Putting phosphates on to start to position the ring to shrink so that we can get to a good precursor to slice the molecule in half and give both of the structures, the Gaap and the Dhap. Those are 2 critical structures to kind of understanding the metabolic pathway, both in the forward direction and the backward direction. Anyway, I've spoken for long enough, so I'm going to end it here. Have a great night or day, whatever time you're watching this. And thanks for going through the carbohydrate metabolic journey with me. We'll see you later.